Section: Introduction. In this section, we discuss how advanced language models, LLMs, have been trained on public text, but the benefits from adding more web-scraped data are decreasing. We see potential in using carefully curated synthetic data to enhance reasoning, which is crucial for improving code generation and solving mathematical problems. Recent models like Llama 3.1 and DeepSeek R1 show that training on reasoning traces along with supervised fine-tuning on selected data can significantly boost model performance. Their success in coding and math tasks illustrates the value of well-curated synthetic data. For smaller models, such as Llama and Gemma, we find that distillation combined with fine-tuning on reasoning datasets has become the main method for post-training. However, distillation requires larger models, and reasoning training needs extensive external datasets. This leads us to question whether smaller models can learn to reason using only data they generate themselves. Previous attempts at recursive fine-tuning on unfiltered text have led to model collapse, where models lose knowledge and produce incorrect outputs. These earlier studies focused on simple text generation, which lacks a clear metric for quality. We differentiate between mode collapse, where a model produces fewer diverse outputs, and model collapse, which involves a decline in overall performance. Our method, recursive supervised fine-tuning on self-generated reasoning traces, might seem at risk of mode collapse since models may prefer confident answers. However, our results indicate that while the accuracy for the best answer improves significantly, the diversity of answers remains stable, suggesting we can maintain variety while enhancing reliability. By using correctness-based pruning, we aim to prevent both model and mode collapse while benefiting from iterative refinement to improve reasoning. We explore how smaller models can enhance their reasoning skills without outside help. Our findings show that selecting reasoning traces through pruning can lead to notable performance improvements. Factors such as the model size, the amount of synthetic data used, the pruning strategy, and the number of fine-tuning rounds all play a role in this process. We break this process down into 3 steps: think, prune, train. In this framework, we prompt models to reason systematically, filter out incorrect outputs based on correctness, and then fine-tune the model using its validated solutions. By applying this approach to smaller models, we achieve reasoning performance that rivals larger models on coding and math tasks. For instance, on the GSM-8K benchmark, we see significant improvements in performance for various models. Our contributions include demonstrating how to avoid model collapse during self-training, providing insights into factors that influence self-improvement, and evaluating our think, prune, train framework, which supports structured reasoning and effective self-improvement. In related work, we note that supervised fine-tuning and reinforcement learning share similarities. Recent studies suggest that supervised fine-tuning can be viewed as a process similar to reinforcement learning, where updates occur on fixed data rather than evolving policies. This aligns with our method of fine-tuning on correctness-filtered data without explicit policy optimization. We find that filtering for correctness and fine-tuning on self-generated sequences can approximate policy gradient updates, indicating that our approach is not just a heuristic but an implicit reinforcement learning strategy, where correctness acts as a reward signal for model improvement. Section Summary. In this section, we explore how state-of-the-art language models can enhance reasoning capabilities through a structured approach called Think, Prune, Train, TPT, which involves iterative fine-tuning on self-generated reasoning traces while employing correctness-based pruning to avoid model collapse. Our findings indicate that smaller models can achieve competitive performance on coding and math benchmarks by effectively leveraging curated synthetic data and maintaining diversity in their outputs. Section: Think, Prune, Train. In this section, we systematically explore the essential elements that facilitate effective self-improvement without relying on external models or datasets. Several factors influence the success of self-improvement techniques, including choice of base model. We concentrate on the Gemma and Llama model families, particularly the smaller versions. Prompting strategy. We use chain-of-thought prompting with a temperature setting of 0.8 to create data from our training sets. Dataset size. We investigate how different amounts of synthetic data affect the results of fine-tuning. Comparison with distillation. We assess how our self-generated data performs compared to data produced by larger models. Fine-tuning rounds. We look at the impact of fine-tuning the base model just once versus doing it multiple times. Pruning strategy. We evaluate the effectiveness of selecting data based on accurate answers, partially correct responses, and unfiltered generated solutions. While previous research often treats self-improvement as a reinforcement learning problem, which requires explicit reward models and policy optimization, we apply supervised fine-tuning using the model's own generated outputs, carefully filtering for correctness. Our analysis investigates whether we can achieve iterative refinement solely through structured data selection. A significant challenge in assessing iterative self-improvement is distinguishing between improvements in the model's reasoning abilities and those resulting from training on a larger dataset. To address this, we tested various data retention strategies during fine-tuning. Initially, we considered keeping multiple solutions for each question across rounds, which allowed the model to learn from a wider range of responses. Although this approach improved performance, we realized that the enhancements might stem from the increased data size rather than true iterative refinement. To better isolate the effects of self-improvement, we decided to keep only one unique example per question per round, ensuring a constant dataset size throughout iterations. Additionally, instead of accumulating data, we replaced the dataset in each round with newly generated solutions, so each model was trained exclusively on its own generated data. Our findings indicate that with strict data limitations, iterative fine-tuning can yield significant improvements, showing that model enhancement is not just a result of dataset growth. We developed a straightforward yet effective method for model self-improvement, which we outline in our algorithm. Regarding how our approach differs, previous self-improvement methods like REST and the post-training setup of Llama 3.1 refine models by applying their processes to already fine-tuned models. REST prunes self-generated data using a learned reward function, while Llama 3.1 uses direct preference optimization and prunes data based on reward models and ground truth filtering. STAR employs rejection sampling and fine-tunes the base model on both correct and corrected rationales, incorporating backward reasoning. However, STAR does not iteratively fine-tune on its improved model. Our method focuses exclusively on supervised fine-tuning to determine if a model can iteratively enhance itself using correctness-based filtering as the sole selection criterion. By concentrating solely on supervised fine-tuning and avoiding reinforcement learning, reward models, and external corrections, we clarify the role of structured data selection in self-improvement. In our experimental setup, we examine the effectiveness of instruction fine-tuned versions of the Llama and Gemma model families, specifically testing Gemma 2-2B, Gemma 2-9B, LLAMA 3.2-1B instruct, and LLAMA 3.3-70B instruct. We use a learning rate of 1/1,000,000th for Gemma and 100,000th for Llama to ensure training stability. The Atom W optimizer is employed with default weight decay, and training occurs over a single epoch with a 10% warm-up to prevent overfitting. The appendix includes synthetic example solutions from question 20 of the GSM-8K training set, showcasing the reasoning steps taken by different models. For our iterative fine-tuning experiments, we set the number of pruned examples per round to 2,000 for GSM-8K and 1,000 for code contests, performing up to 4 rounds of iterative improvement. Evaluation is conducted at a temperature of 0.7. For GSM-8K, we select a subset of 500 questions from the test set, ensuring that answers match the ground truth exactly, including formatting, to maintain both correctness and adherence to the expected answer format. Additionally, we assess our recursively trained models on 140 questions from code contests that do not include image tags, using standard input-output matching to verify correctness. Section Summary. In this section, we systematically investigate the components of effective self-improvement in models, focusing on base model selection, prompting strategies, dataset size, and pruning methods, while applying supervised fine-tuning to enhance model performance using its own generated outputs. Our findings indicate that iterative fine-tuning can yield meaningful improvements without relying on external data or reinforcement learning, emphasizing the importance of structured data selection. Section: Results. In this section, we present our results, which are divided into 3 parts. First, we analyze how the size of the dataset and the model that generates the data affect fine-tuning results. Next, we assess the Think-Prune Train process on the GSM-8K and Code Contests datasets. Finally, we validate our pruning strategy, showing that pruned synthetic data performs better than unpruned data and that our method works well with different llama model versions. Regarding synthetic data scaling, we explore whether larger synthetic datasets and the models used to create them lead to better performance. Our experiments show that simply increasing the amount of synthetic data does not always improve results for all dataset types. We also compare the effects of fine-tuning with increasing amounts of human-generated data. For GSM-8K, we find that small amounts of synthetic data from the larger Gemma 9B model outperform those from the smaller 2B model. Specifically, with 2,000 examples, the 9B model achieves a pass at 1 score of 54.0%, while the 2B model scores 52.5%. However, as we increase the dataset size, performance levels off or even slightly declines for both models. This suggests that scaling data is not a one-size-fits-all solution. Performance depends on the quality of the data, its size, and the model used for generation. Next, we look at how recursive synthetic data generation affects performance across various tasks. We notice cumulative improvements, especially in single-attempt performance. Our approach differs from others because we start with basic instruct models and encourage them to develop reasoning skills, rather than using models specifically trained for reasoning. In terms of mathematical reasoning, we see significant improvements through recursive fine-tuning, where each new model is trained on synthetic data from its predecessor. For example, the Gemma 2B model's pass at 1 performance on GSM-8K increases from 41.9% to 57.6% over 4 training iterations. The Gemma 9B model also improves, reaching a pass at 1 of 82.4% from 66.4% in 3 iterations. While pass at 1 consistently rises, pass at 2.0 shows diminishing returns, suggesting that recursive training mainly boosts accuracy rather than diversity in the generated samples. We believe that the reasoning-heavy nature of mathematical tasks allows recursive fine-tuning to build on previous patterns, which aligns with findings from other studies on structured reasoning. In the code generation area, we observe more complex results. The pass at 1 performance in code contest improves, but pass at 5.0 levels off. The 2B model's pass at 1 score increases from 0.9% to 1.14% after 4 recursive training rounds, while pass at 5.0 stabilizes around 7.85% to 9.2%, likely because code generation relies less on step-by-step reasoning. We also used a smaller dataset of 1,000 examples for each recursive round, compared to 2,000 for GSM-8K, due to the smaller size and lower accuracy of the model on that dataset. We find that pruning is essential for the quality of self-generated synthetic data, directly affecting model performance. Experiments with unpruned data show worse performance, while pruning helps models trained on both 2B and 9B data achieve similar results. Without pruning, the 9B data significantly outperforms the 2B data across all tasks, highlighting pruning's role in balancing data quality. Our soft pruning experiments, where we retain examples that pass certain tests, also show increased diversity. In summary, our results reveal differences in learning efficiency across model sizes when using the Think-Prune Train method. The smaller Gemma 2B model needed 4 complete rounds of recursive fine-tuning to reach peak accuracy, while the medium-sized Gemma 9B improved faster after 3 rounds. In contrast, the much larger Llama 70B model achieved a pass at 1 accuracy of 91.5% after just 1 round of fine-tuning. This high pass at 1 score indicates that our method effectively enhances reasoning abilities, even with minimal training iterations for larger models. These findings emphasize the importance of considering model size when designing training strategies. Section Summary. In this section, we analyze the impact of dataset size and model type on fine-tuning outcomes, revealing that simply increasing synthetic data does not guarantee better performance, as quality and model interplay are crucial. We also demonstrate that our pruning strategy enhances synthetic data quality, leading to improved model performance, particularly through recursive fine-tuning, which significantly boosts reasoning capabilities across various tasks. Section: Possible mode collapse. In this section, we discuss the potential for mode collapse in our recursive synthetic data generation. Our improvements in pass at 1, along with stable pass at 2.0 and pass at 5.0 metrics, indicate that the model may be favoring high-confidence solutions over a diverse range of outputs. Mode collapse happens when a model focuses on a limited set of high-probability results, sacrificing variety. Previous research has examined this issue, particularly regarding how training models on their own synthetic data can lead to a narrowing of output distributions, resulting in less diverse and potentially lower quality results. While those studies highlight the risks of feedback loops, especially in creative tasks, our situation is different because we have a clear definition of correctness. We notice a decrease in output diversity but an increase in accuracy, which is not necessarily a negative outcome, especially in fields like mathematics and programming where correctness is crucial. Although we see less variety in our outputs, the improved accuracy aligns with our aim to enhance precision through pruning. This effect may also be linked to how fine-tuning influences hallucinations. If diversity were our main goal, we could use methods like soft positive sampling or data accumulation, but our iterative approach naturally leads to more high confidence and precise outputs.